Okay, so like I said, we're going to do this last trick from calculus of residues. Sort of an odd thing to do, but we're going to do it. So evaluating some infinite series using the calculus of residues. So you want to evaluate something like this. You're looking to evaluate some function, at the integers, this infinite, doubly infinite sum. So what will be useful is to introduce sort of a sort of helpful function. And that will be this guy. G of z will be pi cotangent pi z. So pi cosine pi z over sine pi z. So you choose this guy. So you observe that, of course, cosine pi n is plus n minus 1. Sine pi n is 0, right, at each integer n. And further, if you take the derivative, right, if you take the derivative of sine pi z, it's non-zero at each integer. Right? And so what this tells you, what does this tell you? This tells you that the thing that we created has simple poles at each integer. Right? So we have simple poles at each. I'm going to use the PQ theorem, the residue of cotangent pi d is going to be at z equals n. It's going to be cosine evaluated at n, cosine pi z evaluated at n, and then the derivative of sine pi z, let's say cosine pi z evaluated at n, okay, which turns out to be 1 over pi. So you use your P over Q theorem, you get the residue of this guy, and so what's the residue of G is going to be pi times that. So it has a residue of 1 at each simple pole at the integers. So G has residue 1 at each integer. Okay. So this function is going to be handy.
Is that sine of pi n, or for pi?
For this one here?
Yeah.
Sine of pi n.
Where is this sine of pi z?
Right here?
Yeah.
Well, what I mean is, if you take the derivative of this guy at z equals n. Sorry, it was very bad notation. Almost incomprehensible with that notation. So that is this guy. The derivative of the denominator evaluated at z equals n is okay. So now, say f is an analytic function with a finite number of poles. finite number of poles. Then, if we look at the product, G times F, it has singularities at most at the singularities of F and the singularities of union the singularities of G. Singularities of F union the singularities of G, which is the integers. We'll call the singularities of F S. So S union Z. For the let C sub n be the following square. So it's going to go out to n plus 1 over 2, n plus 1 half, negative to n minus n half. Okay. So that's its diameter. And this square here. Okay. So here is n, here's negative n, here is n, here's negative n. It's just a half beyond that. Just to trap all these guys inside. Okay, so now we're just going to do something very simple. This is not. There's no real special insight that happens at this point. Then, by the residue theorem, obviously, the integral over Cn G F is going to be 2 pi I times the sum of the residues of GF inside there. Right? So the residues of G times F over all Z in S plus the guys, the singularities that are at the integers, but weren't singularities of F, because we don't want to double count these things. Okay. So just all this is saying is that 2 pi I times the sum of the residues, all the residues inside sigma. Okay. So nothing has happened yet, and nothing will continue to happen for some time. Yeah, in fact, this is not all that exciting. So, but anyways, I don't know. It's sort of the application is cool, I guess. Okay, so so now we're going to create a theorem, but it's not really a theorem. It's sort of just an obvious consequence of the residue thing. So in that case, using the above notation, if the limit of n goes to infinity of Cn G F is 0, then the limit of n goes to infinity of summation f of n, where n lies between negative n and n is not a singularity of f, equals negative the residue of G times f at the singularities of F. Okay. All we're saying is that if this is 0, then these two must sum to 0. So it's just elementary school. It's an elementary school statement. If 0 equals a plus b, and a equals negative b. Sorry to expose you to elementary school mathematics. Okay, right, but is that clear? Right, that's So by the residue theorem, we have this. Right, if the limit of this is 0, then the limit of this thing is going to be the negative, the sum of all the limit of this thing, that's this left-hand side, would be negative the sum of the residues of GF at the singularities of F. Okay. Anyone have questions? Any questions at this point? Yeah, hold on. Yeah.
Why do you take the limit on the right first one?
Well, because it's finite. Because we said, so we said here that there's a finite number of poles. So we don't need, there's no, you could say the guys who are inside Cn as n goes to infinity.
Right.
But, after a certain point, it's just going to be this number. Yeah. But if it weren't finite, then you need to say something like this. Okay. Okay, so this theorem, is basically just an application of the residue theorem. Maybe to make it a little bit more interesting, we should give a condition. We will give a condition to say when we can use this theorem, right? So to imply this point. Okay. So. And this is not that fantastic, but it's okay. So again, when can we use this theorem? Here's one condition that will do it for us. Let F be as above. So it's analytic. C excluding finitely many singularities. If outside of some circle, z times f of z is bounded, then we can use the theorem. Then the limit of gf of cn is going to be we'll examine this more closely in a second and see what that means. But before we do, let's get the application. So if we let f of x be 1 over z squared, if we let f of z be 1 over z squared, then z times f of z is 1 over z, which is bounded outside of any circle. So then the proposition and the theorem apply. So of course this thing has a double pole at 0. what we're going to do is apply the theorem to this, and this will give us the result that we advertised at the beginning. So, some algebraic manipulation of the series for sine and cosine. Algebraic manipulation gives that if we look at g times f, then it's 1 over z cubed minus I squared over z times 1/3 plus some other stuff. The only thing we need from this is the residue. Okay, so you just do some algebra and try to get the first few terms of the Laurent series. You've done this sort of thing in your homework. Right? And so the residue of g at f is negative pi squared at s equals 0. And then you just apply the theorem. Right? The theorem says then that the limit as n goes to infinity of summation n between negative n and n, as long as n is not the singularity of f, right? As long as n is not equal to 0, right? And this limit is pi squared negative pi squared over 3. Right? And same sort of thing as with the principal value integrals, right? We have an even function here, right? So this tells us that summation n equals 1 to infinity converges. Converges, and in fact is half of that. So same warning as before. Like this is sort of like a principal value sum, right? Akin to the principal value integral, right? So its convergence doesn't necessarily imply the convergence of the true of this thing, for which you would need the sum from 0 to infinity and from negative 1 to negative infinity to converge, right? But since it's an even function, then it does. Okay. So calculus of residues gives you this proof of this famous fact. Any questions about that? We'll prove the proposition in a second. Any questions? Yeah, Christian.
Sorry, just coming back here to this theorem that supposedly doesn't do anything. On the bottom here, shouldn't the left? How is the left side equal to the residues of g times f over not the set?
So these are the guys. Remember, this thing on the left is this thing here.
Yeah.
The guys who are in Z, who are inside of C sub n, right? The guys who are in C sub n, the integers who are inside C sub n are negative n up to positive n, right? So what I could write here instead of this is Z is all the n between negative n and positive n, as long as they're not in S, right? And so that's maybe more akin to what I meant.
Yeah, I get that. But then how does the limit turn into the residues of g times f?
So, right, if this thing goes to 0, right? So take the limit of both sides, right? Take the limit as n goes to infinity of g times f c sub n take the limit of this thing, you get, this will turn into the residue of G times F, Z and S, plus the limit as n goes to infinity of summation negative n between n is minus s of the derivatives of G times F. Right. So right now, I'll take, so we had this fact. Let's take the limit as n goes to infinity of it. Okay. If this thing is 0 on the left, right? So now let's say this thing is 0. So this equals 0. In that case, 2 pi I times this thing is 0. So that means that this is equal to negative this, right? So that's what I'm saying here. Oh, what am I doing? Oh yeah, no, that's right. So yeah, sorry. So the residues of G times F at these guys. What are the residues of G times F at the integers? Remember, the residue of G was 1, right? And we can multiply it by the residue of G at z equals n was 1. The residue of G times F at an integer is going to be 1 times the value of F there. Right?
Yeah, I'm not sure that's
Right? So, right? So, right? G, what was G? Remember, G was this thing. It had a simple pole. So if we look at the Laurent, expansion, right? So consider the Laurent expansion. G at z equals n, right? It's going to be, it's going to be 1 over z minus n, right? Plus some higher order terms, right? Okay, and then you're multiplying it by f. You're multiplying that thing by f, right? Where f is something that f is an analytic function, right? F is analytic. We're not at a singularity of f, so you multiply it by some function that's analytic there, right? Well, what's going to be the residue at that point? Well, it's going to be f of n, right? You're going to get f of n. It'll be f of n.
Yeah.
Right.
Okay.
Okay. Yeah. Okay. Okay. So yeah, I guess it wasn't completely obvious. Okay. Does that make sense?
Mm-hmm. Yeah.
Anyone else? Does that make sense to everybody? Okay. So So let's go back then to the proof of this thing, and this will require a little bit of we'll have to get our hands a little bit dirty. Which I think is the merit of including this thing. Okay, so back to what we need to get our hands pretty dirty. So we'll get this the whole way. that clear? Is that thing clear? Right? You know, you have this. You have an analytic function, right? And you're multiplying. Right? You have this thing which is a pole of order 1 there, right? So what's going to be the residue at z equals n? It'll just be f of n. Okay, so let's go back to this proposition, right? We're trying to show that this limit is 0. So the first thing we're going to do is we're going to make an observation about the Laurent expansion. So consider the Laurent expansion. So we're given that this is smaller than this is bounded for all z outside of some disk, right? So that tells us that if we look at 1 over z, f of 1 over z, that's bounded for 1 over z. I'm sorry, for z being less than 1 over r. So you have a function in z that's bounded, right? And so what does that give you? That says that this thing has a power series expansion, right? And 0 is a removable singularity, right? So 0 is a removable singularity for this function. So we know that f of 1 over z has Taylor expansion in z less than 1 over r. Okay. What does that give us? That gives us that f of z for z bigger than r. This tells us something about the Laurent expansion, right? That f of z, right, is going to be greater than 1 over z to the n from n equals 0 to infinity, right? Or allow me to divide both sides by z, you get this. Alex, are you okay? Yeah. You look down. Are you down? Yeah. Don't be down.
It's not the lecture.
Okay, good.
The lecture is great.
Okay.
The lecture is bringing me up.
Okay.
Yeah.
Okay, good. I'll try to make it even more. I'll try to make it better. Okay. Yeah, actually, it will get even better. Okay. Yeah, I mean, this part here to me is sort of a high point, but it actually gets better than that. Okay. So what do you see? You see that your Laurent expansion doesn't have any power. It doesn't have a constant power. It doesn't have a power of z. Right? Basically, it has only the principal part. When you divide the Laurent expansion into the principal part and the thing that looks like a power series, right? That power series part is gone. Right? We don't have that. Okay, so that's what this is doing. This is doing to us, and that's why 1 over z squared was okay for it, right? Because this has only a principal part. There's no polynomial part. Okay. Okay, so that's the observation, right? That the Laurent expansion doesn't have this the Taylor series part to it. So that's part one. Part two, we're going to make sort of a cool observation, which is that if we look at pi cotangent pi z over z dz, the integral over c sub n, we actually get 0. We always get 0. This observation will seem sort of like, why it should seem sort of confusing at this point. Like why do we care about it? But you'll see in a second why we do. So so plane is true. Well, again by the residue theorem, the integral is going to be 2 pi I, of course, times the sum of the residues of the function at z being at z equals 0 plus or minus 1 plus or minus 2 plus or minus n. Right. Those are the singularities. Those are the singularities of this thing that lie inside of C sub n. Okay. So okay. So now here we make a sort of clever observation, which is that at z equals 0, right? At z equals 0, we have a pole of order 2, where we have pole of order 2. Right. We observe that since the Laurent expression, since the function is odd, right? We have this odd function. All the odd coefficients in the Laurent expansion about 0 must be 0. Right? All the coefficients in the Laurent expansion have to be 0. Right? Is that clear? I mean, if you think about it, right? You know that your Laurent expansion looks like this. Right? Looks like this. But you know that that's equal to a minus 2 z to the negative 2 minus a to the minus 1 z to the negative 1 plus a naught minus a1 z blah blah. Right? So you have another Laurent expansion, but the Laurent expansion is unique, right? So that tells you that this and this must be the same thing, right? And so this must be 0. All the odd coefficients must be 0. Okay. So in particular, the residue of this guy that z equals 0 is 0. So the one in the middle is 0. And then, yes?
Wait, why do you know that there's this alternating, you can express the Laurent series as this alternating form, like this negative positive?
Because the function is odd. So you know that if you put in z minus 1 here, if you put in negative z here, you're going to get the same thing. Right. So it's just a clever observation. Okay. Now for the other guys, for plus or minus n and not equal to 0, we know that we saw earlier that the residue of pi with 10 pi z was 1 at each guy, right? Was 1, so the residue of pi cotangent pi z over z at n is going to be whatever at z equals plus or minus n. It's just going to be 1 over plus or minus n, right? So at at 2 it's going to be a half. At negative 2 it's going to be negative a half, right? And so the residue at 2 and negative 2 cancel each other out, right? And so all these guys will just sum to 0, right? Because you have plus or minus 1, plus or minus 2. Okay. So summing it all together, z equals plus or minus 1, plus or minus 2, etc. And then altogether it's okay, so now comes the good part. Okay. So, and it's going to use parts 1 and 2. So parts 1 and 2 are just to set us up for how we're going to control the integral. Right. Analysis is all about controlling things. It's a bad practice for one in real life. But in analysis, that's all you do. You just try to control things. You break everything into little pieces, and you try to control all the little pieces so that it all works together. It's almost a prescription for like a ill-fated future. But yeah, like you're almost dooming your future relationships, or becoming an analyst. But anyway, yeah, my favorite TA from college is a teacher at Reed now, and if you look at his website, he has a quote from I forget. There was some Russell Crowe movie about somebody at sea, like a you know what I'm talking about? Like somebody who is a pirate, or I forget. Anyway, there's he has a quote on his website that I find particularly apt, which says something to the effect of, like, teaching is a dismal profession. Schoolmasters are constantly surrounded by people who they talk down to and come to regard everybody else as being inferior to themselves. Have you ever met a schoolmaster fit to associate with grown men? I never have. Right. It's like teaching is a dismal profession and like injurious to the soul. Yeah.
Wait, why?
Well, because you don't talk to people as equals. You spend the bulk of your life talking to people not as equals, right? And then you come to get into that habit of not talking to people as equals. It's dangerous. It's quite dangerous. You have to be cautious, right? Because you're always like, you have always, using, if you don't keep in mind that none of this is your own work, right? If you don't keep in mind that none of this is your doing, right? Then you can delude yourself.
I guess it just depends if you look down on people who are naive, because it's not it's not a lack of intelligence; it's just a lack of knowledge.
Right. So yeah, so one has to keep one's perspective. Yeah. Yeah, so for those of you hoping to become professors, watch out. Yeah, the really great mathematicians, that I know are, at least I think most of them are pretty humble people. My own advisor, when I told him in my second or third year of graduate school that I felt stupid all the time, he said, "Welcome to mathematics." Right? That's how you're going to feel all the time. That's how you're going to feel all the time. Right? And he was no slouch. Right? He was. Those of you who had classes with me before know. So my advisor was Bob Pepperman. So there's he's the younger brother of Charlie Pepperman, who is the Fields Medalist. Charlie Pepperman is sort of legendary. The story, and I don't think this is quite true, but the story is that Charlie Pepperman, finished his PhD at Princeton when he was 19. Then was immediately made a full professor at the University of Chicago, and then 2 years later, came back to Princeton as a full professor, where he's remained since. So I don't know how much of this is true, but he's smart. And if you go to the University of Chicago, I think there's some evidence for this story. I mean, you can probably just, these days you can probably just look on Wikipedia to find out. But if you go to the University of Chicago, on the third floor of the math building, there are these pictures, like the assistant professors from, whatever date it was, the associate professors and full professors. And like it's the younger guys and sort of older guys. The full professors are all these sort of old-looking white guys, except for this one boy. And that's Charlie Pepperman. Anyway, so Bob Pepperman is the younger brother, and I've said this before, but being a late bloomer, I think he got his PhD when he was 24 or something. I'm not sure when he became a full professor at the University of Chicago, but anyway, so he, a smart guy from a family of smart guys, and if he said he feels stupid all the time, that's probably how we should feel. That's probably the right way to feel. And if you feel stupid all the time, okay, that's all right. Right? That means you're probably doing the right thing. Right? Probably means you're doing the right thing. Or you've got the right perspective. Okay. Boy. So let's get the let's control the integral. So step 3, controlling the integral. Okay. So we use the notation from step 1 that f of z looks like this: a naught over z plus a1 over z squared, plus et cetera, et cetera. That has only a principal part to it. Okay. So if we call by step 1, f of z looks like this. By step 2, we pull these things out immediately. You can actually, if we look at this thing here, the integral over Cn, we can actually subtract off subtract off a term like this, right? Because we know that the integral of pi cotangent pi z over z is 0. Right? So all we've done is subtract off a 0 term. Right? A very clever looking 0. Right? Please say. This is 0. Just to make things a little bit more humorous, the way that my graduate school experience went with Professor Pepperman was sort of like this. I'd come in and he'd say, well, here's something that I've been thinking about and I can't understand it all. I can't figure this out at all. I'd like you to think about it. And inside I'd be thinking, you can figure it out. Okay, and then I go off and I think about it for several months, sometimes even a year, and I come back and say, I'm sorry, Professor Friedman, I can't make heads or tails of what you're trying to get at here. I say, that's okay. Here's another thing that I've been thinking about, and I can't figure it out at all. So this went on for several years, and then I finally figured out something. And graduated. Yeah, because if you don't graduate. Okay, so now we want to let's look at this thing, and we will control the integrand. Okay. So f of z minus a naught over z, using it above, right, looks like 1 over z squared times a1 plus a2 over z plus a3 over z squared plus etc. Right? And that is valid outside of this disk. Right? So we don't have to do this, but it's convenient to think like this. Now, if we look at let w be 1 over z, if we consider a1 plus a2w plus a3w squared, etc., this is analytic in w less than 1 over r squared. 1 over r, excuse me. 1 over r. And thus bounded on w less than or equal to 1 over r prime, for some r prime bigger than r. Right? It's analytic on this open disk. We restrict it to a closed disk. It's going to be bounded there because we bounded on the closed bounded set. That continuity. Okay. So what does that tell us? Switching back to the original notation, that tells us that so a1 plus a2 1 over z plus blah 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 is bounded by some m on z greater than r prime. Okay. And so, if we take the actual value of f of z minus a naught, that's bounded by m over modulus of z squared outside of the r prime matrix. So that's the bound on the integrand that we get via steps 1 and 2. Via step 1. Okay, and then that's the bound that we want. That's the bound that's going to be useful to us. So then, returning to the integral, we see that the thing that we're trying to bound which we saw was equal to this thing, right? We can control. It's just controlled by. I'm gonna move these things in. Right, this is bounded by pi. We know that we have a bound on this thing, right? It's m over z squared. Right? But z is bigger than, right? Z is bigger than n plus 1/2, and the modulus of n plus 1/2 because we're on c sub n. So our z squared, 1 over z squared is smaller than 1 over n plus 1 modulus squared, 1/2 modulus squared. And then we get that thing times the perimeter of Cn. Okay. So you get 8 times n plus 1/2. So we just call this n plus 1/2. It's positive. Right. And then we have something, this primum of cotangent on Cn. Okay, so that's our bound on the integral. Any questions? So the book leaves this as an exercise, and I will too, to see that this is bounded by 2. They give some hint as to how to do it. Then as n goes to infinity, this goes to 0. So that's the analysis that gives you the condition that allows us to apply the theorem. Any questions? Any questions on how we did it? So, there's 13 minutes left. We could start the section on analytic configuration. Oh, right.